Hey there, we're going to go over some introduction to impulse and momentum notes. And we're going to start out talking about momentum. Momentum, we can basically describe that as moving inertia. And we talked about inertia earlier in the year, and we said that an object's inertia is mainly determined by the mass. So it's an object with a mass that's in motion, it's moving. And the equation that we have for momentum, we have P, a lowercase p, is equal to mv. So the m here stands for the object's mass, and that's in kilograms. The v here is velocity, and that's meters per second. And the lowercase p, that stands for momentum. Now we couldn't use an m, right, because we already use m for mass. So it's a lowercase p, and the unit is just kilograms times meters per second. So we don't have any new unit here like we did in the forces unit. If you remember the forces unit, we had 1 kilogram times meter per second squared, which was a Newton. But now for momentum, it's just kilograms times meters per second. There's another unit that we'll see for momentum here in just a little bit. And let's look at a couple examples and just applying this new equation. So the first one says we have a 70 kilogram football player and he's moving at a velocity of 2 meters per second, and we're going to calculate his momentum. So we'll write down what we know. The mass is 70 kilograms. The velocity is equal to 2 meters per second. And we're trying to find the momentum, P. So we have our new equation, P is equal to mv, and we're going to just plug those numbers in. So I have 70 kilograms times 2 meters per second. So the momentum of this player here is just 140 kilograms times meters per second. Now that's finding the momentum of one object. Let's look at a system here that consists of two objects. So we have a 50 kilogram object, it's moving 30 meters per second. And then we have a 45 kilogram object that's moving 20 meters per second. And we want to find the momentum of this system. So we're going to write down what we know. Since we have more than one object, then we want to kind of be able to identify those objects. So I'm going to say M1, that's a mass of object 1, is 50 kilograms. V1 is equal to 30 meters per second. My M2, the mass of object 2, is 45 kilograms. And the velocity of object 2 is 20 meters per second. And we want to find the momentum of my system. So to do that, all we're going to do is take the momentum of object 1 and add it with momentum of object 2. So the momentum of the system here will be the momentum of object 1 plus the momentum of object 2. So let's start with object 1. We had 50 kilograms times 30 meters per second, which gives us 1,500 kilograms times meters per second. And for object 2, we had 45 kilograms times 20 meters per second, which gives me 900 kilograms times meters per second. So the momentum of the system here is just going to be the 1,500 plus the 900 kilograms times meters per second. So that gives me 2,400 kilograms times meters per second. Now, where you have to be careful is, if you remember, sometimes we can have a negative velocity. So let's say, for example, I have a cart and it's moving to the right. And then I have another cart in this system and it's moving to the left. Well, this cart would have a positive velocity. this card over here is going to have a negative velocity. And so because it has a negative velocity, that's going to end up being a negative momentum. When I add those up, I'm going to end up actually subtracting them. So just be aware, okay, be careful with your positives and negatives here. Okay, if they're going in opposite directions, then one's going to have a negative momentum there. All right, so let's go back up here. And if you remember last unit, we started talking about a system, right? We brought in a system into some of our problems. And remember, the system was just a collection of objects. So on that last problem, my system was two objects. Now we're going to go a little bit further with that, and we have what's called a closed system. And a closed system, it is a system that it's a physical system that doesn't exchange matter with its surrounding. It's not influenced by any outside forces. And so the result of that is our net force on the system is equal to 0. There's no net force on that system. And so that means that your momentum of the system is conserved. So it doesn't change. So in a closed system, the overall momentum of the system doesn't change. Now the momentum of the individual objects within the system can change, but the system as a whole, it's going to be conserved. It's not going to change. But sometimes we might have a system where there is a change in momentum. And so we're going to kind of look at that and see what causes that change in momentum, and that is called an impulse. So an impulse causes a change in momentum. And how I can describe an impulse, it's a force exerted for a period of time. And the equation that we get built from that, since it causes a change in momentum, so remember this delta symbol that just means change. So I have a change in momentum is going to equal an impulse, which is this net force exerted for a period of time. And so this is the equation that we have, and we call it our impulse momentum equation. Okay, a change in momentum is equal to an impulse, which is that net force exerted for a period of time. And remember, the unit for your force here is newtons, and the unit for time is seconds. And so the unit for impulse then would be newtons times seconds, which is the exact same thing as kilograms times meters per second. So either one of those would work for momentum, just depending on the problem and the numbers that I'm working with. Now, if I'm talking about a change in momentum for one object, then my P would equal the mass of that one object, and what's changing is the velocity. So an object whose momentum is changing, we would have this equation here, m delta v. The mass of that one object times the change in its velocity would equal that change in momentum, that delta p for that object. So we could actually substitute that in and have the equation net force times time is equal to m delta v. Okay, so if I'm talking about the change in momentum of one object, we could have this equation here. So let's take a look at an example in calculating this impulse on an object. So this one says we have, or while playing kickball, you have a 1.5 kilogram playground ball. It's moving to the left, underline that there, at a velocity of 12 meters per second. And then a physics teacher kicks it, sending it in the opposite direction with a velocity of 24 meters per second. And we're asked to calculate the impulse exerted on the kickball by the physics teacher. So the equation that we just talked about, since it's a one object, we're trying to solve for this impulse, right? Force times time. And that's going to equal a change in momentum. And since it's just one object, it would be the mass of that object times the change in velocity. And remember, your delta V, your change in velocity, is just going to be the final velocity minus your initial velocity. And for this problem, it started out going to the left, so we'll call left negative. So your initial velocity is equal to negative 12 meters per second. And the physics teacher hit it in the opposite direction, so that means the final velocity is going to be 24 meters per second. So now we can go ahead and kind of plug in to solve for this impulse. So the impulse is equal to the mass of that object, of that kickball, which we said was 1.5 kilograms, times the change in velocity. So the final velocity was a positive 24 meters per second, minus the initial velocity, which was negative 12 meters per second. So 24 minus a negative, that we would end up adding those, right? So it'd be 36 meters per second times 1.5 kilograms. So your impulse is just going to equal 54 kilograms times meters per second. We could also say newtons times seconds right there. Either one would work as far as our unit. So that's how we can apply this impulse momentum equation and solving for the impulse on an object. Now, if you notice though, for this one, it was a constant force. So the physics teacher was applying a constant force, so we were able to go in and solve for this impulse here. But that force may not always be constant. And if that's the case, then we have another way that we could solve for the momentum, or I'm sorry, for the impulse on the object. So we would do that graphically. So let's look at a force time graph. So here's force in newtons and time in seconds. And let's say this is 1 newton and 2 newtons right here. And we'll just say 1, 2, 3, 4, 5 seconds. And let's say there's a constant force for the first 3 seconds. And that constant force is at 2 newtons. So I would have a straight line right there. And then after 3 seconds, I start having a variable force. So it starts changing. And let's say my graph ended up looking like this. And I wanted to solve for the impulse. So what was the impulse on this object? And so to do this, we're going to use that trick that we learned in finding the area underneath the curve. So I'm going to break it into a rectangle here and a triangle right there. And we're going to find the area. So let's start with the rectangle. That's going to be length times width. So that would give me 2 seconds. Oh, I'm sorry, 3 seconds times 2 newtons, which would be 6 newtons times seconds. And now let's look at the area under the triangle, that number 2 there. It would be 1/2 my base, which is from 3 to 5, so 2 seconds, times the height, which is also 2 newtons here. So 2 times 2 is 4, half of that is 2, so 2 newtons times seconds. And now to find the total impulse here, we're just going to add them up. So your impulse is going to equal 8 newtons times seconds. Okay, so if it's a constant force, we can just use our equation Ft and calculate your impulse, or we can find the change in momentum. And then if it's a variable force, then we're going to go to a force time graph and find the area underneath that curve.